I'm going to talk today about the eigenvalue constraint. So let me remind you, so this is joint work with a parlor who should now be almost on the runway, I suppose. So let me remind you that what the situation was. We have this Q tensor, which is defined as a normalized second moment of the probability measure of the molecular orientations. And so it measures so it has this form. It's the integral of p tensor p minus third the identity against the measure. And Q is a symmetric matrix. It's trace-free because we've subtracted off this term. And the minimum because Q plus 1/3 the identity is a non-negative matrix, that means that the minimum eigenvalues have to be bigger or equal to minus 1/3. Okay, the minimum eigenvalue of Q is bigger than or equal to minus 1/3. And let me also remind you, last time we talked about minimizers in the Sobolev space of the total free energy, which is this bulk part, and then an elastic part. And for the elastic part, I took this linear combination of the four invariants. And remember, this one was maybe the more controversial one, and it had a coefficient L4, which there was a story about whether this should be 0 or not. Okay. Right, so now, what I'm going to talk about today is the question of how the eigenvalue constraint is maintained in the theory. Okay. So this is a serious issue. It can be seen from the fact that if you take the usual quartic model for MBBA with experimentally measured coefficients, then the scalar order parameter of the nematic state exceeds 1 for temperatures only 7 degrees below the transition temperature. So this is obviously something that one doesn't want. I want to draw an analogy with, when I first saw this problem, I was immediately reminded of a problem in nonlinear elasticity, which is in fact still unsolved. So in nonlinear elasticity, you pick some kind of reference configuration for the material. So you take some subset omega in R3 and you label the particles by their positions x in this reference configuration, and then considering statics, in some deformation, the point that was at x in the reference configuration gets mapped to y of x in the deformed configuration. So what you have to do is to minimize the total stored energy, or total free energy at a fixed temperature if you like, which is given by an integral of some stored energy function that depends on the gradient of y of x. So it's a 3x3 matrix, just as in the Q tensor theory, subject to some boundary conditions. For example, that you specify y on one part of the boundary to be some given a mapping, and you perhaps leave the rest of the boundary free. Now I just like, this is a parenthesis, which is in elasticity theory, this function w is never a convex function of the gradient. It is never a convex function of the gradient. So that's a contrast with liquid crystals, where we saw that the elastic part of the energy was, at least under the normal hypotheses, if you like, and whether you express it in terms of the gradient of n or the gradient of q, is a convex function of the gradient. Now in multidimensional problems of the calculus of variations, convexity with respect to the gradient is not a natural condition. And we know that the natural condition is something much more complicated and much less well understood, but more general, which is quasi-convexity. And so it's quasi-convexity that plays a role in nonlinear elasticity, and it's a bit strange to me that it doesn't play a role in liquid crystals, where mathematically you would really expect it to. Okay, so I know that's just a kind of aside. Anyway, so back to this problem, nonlinear elasticity. So there's something that's very important in elasticity, and that is that matter doesn't interpenetrate itself. So, for example, if I'm this is the reference configuration of the elastic body. I'm omega, and here's a deformation, right? Now, I do not want my hand to go through my head. Okay, that's not a physical deformation. So that means that y should be an invertible map. Okay. So how do you ensure? So there we are. There's a kind of constraint. So how do we ensure that the deformation is invertible? Well, there's two sorts of points here. There's some kind of global condition about what happens on the boundary and stuff, but there's a local condition. You also want it to be locally invertible, and you would like that the determinant of the deformation gradient was positive, so that you get local invertibility, more or less, at least for almost every x in omega. So there we are. You see, there's a pointwise constraint on the gradient of y. So in this liquid crystal problem, we've got a pointwise constraint on Q, and so the question is, how is this constraint maintained in elasticity theory? Well, what you do is what everybody does is to assume that the stored energy function blows up as the determinant goes to zero. And that's a very natural condition. It says that if you try to crush something to zero volume, you need more and more energy and eventually infinite energy to do that, right? You just can't do it. Okay, so correspondingly, it seems very natural to suppose in the de Gennes theory that in fact the free energy function blows up as the constraint is hit. So that will give you an energetic reason as to why the constraint on the eigenvalues is preserved. Okay, so in fact such a suggestion was made by Jerry Erickson in the context of his model of nematic liquid crystals. And what I'm going to do today is to show how you can construct such a bulk energy on the basis of a microscopic model, indeed one that we've already seen several times. And the interpretation, rather than energy blowing up as you crush something down to volume, is going to be that perfectly aligned states have entropy minus infinity, and they shouldn't occur. Okay. Right, so we're going to use the on-saga model. Well, I'm not sure whether it's always been called the on-saga model, but it's exactly what Basao-Doi showed in his lecture. I'm going to use the Meyer-Saupe interaction. It's exactly the same, but the calculation is going to be different. Okay, so now in this model, the probability measure mu is continuous. Why has this stopped working? So I moved this accidentally. Yeah. Oh, there we go. Okay, so we have a continuous density rho of p, and the bulk free energy at temperature theta has the classical form of the Helmholtz free energy. It's an internal energy minus the temperature times the entropy. And the entropy in this model is given by minus Boltzmann's constant times the integral over the sphere of rho log rho. And what is U? What is the internal energy? Well, with the Meyer-Saupe interaction, that's given by this expression. So there's a coupling constant, kappa over 2, and then you have this double integral with respect to P and Q, points on the unit sphere. Now this 1/3 is not very important, because when you integrate 1/3, since the integral of rho is 1, you just get a constant, but it's put there to get a nice formula at the end. Okay, and so this is saying that this energy here, this internal energy, is minimized when P is parallel to Q. So that's an effect that's somehow trying to make molecules align with each other. On the other hand, the entropy term is trying to disorder them, and so there's some kind of competition between them. Now, one of the things, I suppose maybe the thing that makes this such a useful, an easy sort of theory to manipulate is that in fact u of rho can be shown to be, it's a very quick calculation, minus kappa over 2 times the Euclidean norm of the Q tensor corresponding to rho. So the internal energy depends on rho only through the Q tensor. Okay. So,
how do you define this Euclidean norm of Q?
what this Q, what this U, okay, so right, so I was when we were interrupted talking about this model, and so there's the free energy and the interaction part with this Morris-Saupe interaction is just equal to a multiple of the Euclidean norm of the Q tensor corresponding to rho, which I wrote down somewhere over there, just to remind you what the formula is. Okay, so what's the idea then? So
what is the Euclidean norm of the matrix?
yeah, Euclidean norm of the matrix, trace of A transpose A, where A is the matrix. Sum of the squares of the entries of the matrix. Okay. Right. So here we've got this entropy term that depends, generally on rho, and then this bit which just depends on the Q tensor. So that suggests that what you can do is, given a matrix Q, you can do a constrained minimization. You minimize this function I theta of rho over rho whose Q tensor is Q, the given matrix Q, right? And you see that means that since this is an explicit function of Q, all you have to do is to do this minimization, the minimization over rho. So in fact, this idea was in this paper of Catriel and people that we discovered later, expressed in a somewhat different way. I think it's very consistent with what Professor Doi was saying. In some sense, you have slow variables, and then you do some kind of thermodynamics, given the values of these slow variables. Now, okay, so how do you do it? Well, it's a sort of almost a classic problem. So all you have to do is to minimize this term, the integral of rho log rho. So you're given this matrix Q, which is supposed to be symmetric and be trace free and satisfy the eigenvalue constraints. And then you minimize this J of rho on probability measures. So rho's in L1 on the sphere, which are non-negative and whose integral is 1, subject to the constraint that the Q tensor is our given matrix Q. And it attains a minimum at a unique rho sub Q. Okay, so that's in some sense just a direct method of the calculus of variations. This is a convex function of rho, and it has superlinear growth, and this constraint is linear, so it's more or less straightforward. What's more, you can more or less write down the answer. So the Euler Lagrange equation for J is in fact given in the following way. So you can, without loss of generality, suppose that you've diagonalized Q, so here are the eigenvalues, and then rho sub Q of P is given by this Maxwellian kind of thing, so exponential sum mu I pi squared divided by the integral of that over the sphere, and the mu i's, which are unique, adding a constant to each of them, solve this equation that the gradient of the logarithm of z, the partition function, is equal to lambda I plus 1/3. Okay. So you have to show that the minimizer does satisfy the Euler Lagrange equation. That's just a little bit tricky because rho is bigger than or equal to 0, and this rho log rho is doing something funny at rho equals 0. So you've just got to be a little bit careful, but it's not that difficult. And so then you can take that rho sub Q and you shove it back into the integral of rho log rho, and here's the formula. And so, I mean, rho sub Q, that was rho sub Q, and the logarithm, of course, is just this expression minus the logarithm of z. And now, if you look at, if you go back to that formula here, you see, in fact, that this is equal to this expression. So, putting that together, you get an expression for the bulk free energy as a function of Q, according to this recipe. It's theta kb times this f of Q minus kappa over 2Q squared. And so shoving that all in here, you see you have a semi-explicit formula expressed in terms of the eigenvalues. The only tricky thing is that you got mu i's here, which also appear in the partition function, and to get those you've got to invert these equations to get the mu i's in terms of the lambda i's. Okay. Now, so here's a theorem that f is strictly convex in Q, and indeed it does the job. That the f, okay, so if the f of Q blows up as the minimum eigenvalue goes to minus a third, then of course this will, because this is just bounded, and this is just a positive multiple there. So okay, so how do you do this? So it's sort of I try and give the proof of this. So the strict convexity just comes from the fact that rho log rho is strictly convex. So I won't bother to say anything more about that. Now, so let's suppose that this blow up didn't occur. We'll just use a kind of indirect kind of proof. So suppose that you had a sequence of matrices Qj whose minimum eigenvalue tended to minus a third, but that this expression remained bounded. Well, take the eigenvector Ej corresponding to the minimum eigenvalue of Qj, and you form this. So this expression must be going to 0. That's exactly what this says. But from the formula for the Q tensor, you can write this as the integral over the sphere of rho Qj of P times P dot Ej squared. Now, the fact that fqj is bounded means you got the integral of qj of rho qj log rho qj bounded, and so that means that you can extract a weakly convergent because rho log rho is superlinear growth. You can extract a weakly convergent subsequence in L1 of the sphere. And the rho you'll be able to pass to the limit, and because you have weak convergence, and so since the integral of rho qj is 1, so the integral of the limit rho is 1, and of course Ej, they're just eigenvectors, so we can assume that they converge to a unit vector. And so passing to the limit in here, just passing to the limit, this guy's just going to P dot E squared. And this is this is an integral, so I mean it's just weak convergence will tell you that it goes to this integral of rho p dot e squared dp, which is 0. So what does that say? Well, that says that rho is 0 unless p dot e is 0. So that means that rho is 0 except on the great circle which is perpendicular to e. So rho is 0 almost everywhere, so its integral is 0, but its integral is 1. Contradiction. Okay. And you see here in this proof, in some sense, this interpretation that is blowing up when the thing becomes perfectly aligned, which is not sort of physical, right? Okay. Now you can do better than this. And you can get some quite precise asymptotics on how it blows up. Okay, so so really it's just a question of how f blows up is what you need. And so here's a fairly sharp result. You see it blows up logarithmically. So f is sandwiched between two linear functions of constants on either side, and then you've got the logarithm of the minimum eigenvalue plus a third with a coefficient minus a half here and a coefficient minus 1 here. And these, I think, they're optimal constants, I think. In any case, okay, so this is done by, one estimate's done by sort of taking rho q is the minimizer, so you take some kind of competitor, and that gives you one estimate. And then there's a dual variational principle, which gives you the other estimate. So So anyway, logarithmic growth as you hit minus a third. So so there are some other predictions of this theory. So I take this bulk energy, I do the same calculation that I did for the quartic case, okay, and you get the same. Of course, it's more complicated because you don't know what a CB is exactly. You only know it sort of semi-explicitly, and you get exactly the same result. All the stationary points are uniaxial. There's a phase transition predicted from isotropic to uniaxial nematic, just as in the quartic model. Okay. And if you take the minimizers rho star of I theta without it being constrained, then that corresponds to minimizing this bulk energy over Q. And these were calculated and shown to be uniaxial by Fatkuling and Slastikov and by Pingweng and collaborators. And actually, it was in fact this paper that sort of made us think about this. It's a nice work, whoever did it. Okay, and also it solves this problem sort of trivially in some sense. So you do get existence when L4 is not 0, because you have to make some assumptions on the Li, but you don't have to assume that L4 is 0, because this term I4, which is the awkward one, you see has the form QLK something L something K. So when you've got control on the eigenvalues of Q, you can say that this is bigger than or equal to minus a third times the gradient of Q squared. And then you can absorb that term into the other ones. Okay? And so you get existence of the minimizer. Now, furthermore, you can do an expansion near Q equals 0. This is a similar expansion is also done in the paper of Catriel and co. And because you've just got a coupling constant, one coupling constant, and the temperature, you get some prediction. So you get this kind of expansion here, and you compare it. You can compare it to the quartic model. And so the ratio of these two terms is 8/3, and that gives that these coefficients b over c, as I define them, is supposed to be 1. I think that's right. I was trying to do the calculation again. There was a mistake in this slide, and I tried to do it again this morning, but I'm 90% certain it's 1. Now, so I rubbed out my values of what this is for MBBA and 5CB, because I'm not 100% sure that the calculations are right. But I know what I can say is that it's of the right order of magnitude. It's out by at most a factor of 2, which I don't think is so bad. I mean, it's an extremely crude model, the Meyer-Saupe interaction. And at least you don't get a value 10 to the 4 or 10 to the minus 4, So it's of order 1, and b over c is experimentally of order 1. So I hope to do this kind of calculation for some better potentials somehow, but we'll see whether that's possible. And now, so here's the interesting thing. So now we've got ourselves a bulk energy, which at least I believe in at some level. I certainly believe in the idea that it can blow up as the minimum eigenvalue goes to. I mean, I don't believe in this particular formula too much, but I think it's sort of it's a proof in some sense that is not unreasonable to assume that it blows up as the minimum eigenvalue goes to minus a third, and so now you can imagine shoving this into adding on some gradient terms. So here I've taken the simplest one constant gradient term. There's a good reason for that, which is that I can't do it if I don't make that choice. So and then you minimize this subject to some boundary data. For example, that Q is specified excuse me, on the boundary as a given function Q0 of x, and we'll suppose that Q0 is sufficiently smooth and that its minimum eigenvalue is bounded away from minus a third. So now you see this integrand, excuse me, this integrand blows up as the minimum eigenvalue goes to minus a third. So it's very reasonable to think that the minimum eigenvalue of q of x should be bounded away from minus a third. Okay, and that's what this theorem asserts. Okay, and that's very important that you can say this, and okay, so what is immediate is that this is positive, or strictly positive almost everywhere. But it's very important that you have it bounded away from zero, because otherwise you can't get the Euler Lagrange equation. If you're sitting on the boundary of this constraint, then you won't be able to get the Euler Lagrange equation. So in general, you'll get some kind of variational inequality or something. You don't want that, right? So we really want this, okay? And once you've got it, then it's a solution of it's a weak solution of the corresponding Euler Lagrange equation, but we've got elliptic regularity, and so it's a smooth solution of the Euler Lagrange equation. Okay. Now, so this is a very interesting sort of conceptual thing, I think, if you're not familiar with the calculus of variations. So I say this isn't immediately obvious, since minimizers in the calculus of variations often have unbounded integrands. This is very strange, and so I give you this old example of which I'm unreasonably proud, which I did with Vic Mizell many years ago. And if you've not seen this kind of example before, it is terrifying for what you think is true in the calculus of variations. Okay, this is a one-dimensional problem of the calculus of variations. Okay, now it's a polynomial, so there's no issue about the integrand not being smooth. Now look at it as, so this is the 28th power. There's a story behind this power, but anyway, it's 28. And this epsilon here is strictly positive. It has to be less than some small number, epsilon 0, which is about 0.001. But the point is, it's strictly positive. So if you look at this functional, it is strictly convex in the gradient u sub x. Okay, and in fact, its second derivative with respect to u sub x is strictly positive. In fact, it's bigger than 2 epsilon. And epsilon is strictly positive. So this is what is called in the trade a regular one-dimensional problem of the calculus of variations. Okay. And Hilbert proved, or maybe Weierstrass or Hilbert or somebody anyway, proved that if you have a weak solution of the Euler Lagrange equation for a regular problem of the calculus of variations, and certainly in one dimension, well, I mean a regular problem of the calculus of variations in one dimension, then it is smooth. Okay? However, if you minimize this integral subject to the boundary data that u of minus 1 is minus 1 and u of 1 is 1, then the minimizer is not smooth. Okay? And in fact, if you do it numerically, you know, you do a finite. Okay, so suppose how would you do it numerically? So you do it by finite elements. You split minus 1, 1 into a, you know, finite little intervals of length h. Okay, and then you replace u by a piecewise affine function on that grid. Okay. Well, you don't even have to worry about quadrature because this is a polynomial. You could even calculate the integral exactly for such a piecewise affine function. So not an issue of quadrature or round off or anything else. Okay, now you minimize this subject, you know, over the nodal values for a very, very small but fixed h. Okay, and what you see is that the method converges perfectly and it goes to one of these two beautiful smooth blue curves. The reason there's two of them is because there's a symmetry in this problem, sort of x goes to minus x and u goes to minus u. Okay. So if you just did this on a computer and you believe in computers, there was absolutely nothing that would lead you to think that there was something odd about this problem. But indeed, these are not the minimizers of the problem, and the minimizer has an infinite slope at the origin. So at the origin, of course, du dx is, well, it's infinite, so the integrand is infinite. So in this problem, to minimize the energy, the integral, it pays to have the integrand infinite somewhere, which is, you know, a little bit surprising. You know, so why does it pay to have the integrand infinite somewhere? Well, because if you have the integrand infinite somewhere, you can make it smaller somewhere else. It's a sort of tautology. Of course, that must be the case. Otherwise, what I said wouldn't be true, right? So if you make it infinite somewhere. So in this case, if you make it infinite here, you follow x to the fourth equals u to the sixth more easily, and this whopping great power of the derivative is going to give you a much less much less to the integral. Okay, so in particular, there's a big story associated with these kinds of examples, and so in particular, it is not true that the minimizer of a regular one-dimensional problem satisfies the the weak form of the Euler Lagrange equations. This is not true. Okay, of course, it is a smooth solution to the right and left of x equals 0, but it is not a weak solution of the Euler Lagrange equation. So that's a slightly worrying thing. Now, so another lesson you can draw from this is something I said in the first lecture, that you could here's a functional, right? So this suppose that this was not an academic example and it had come from some physical situation. Okay, so now you can see that if you minimize this functional in two different, apparently quite reasonable spaces, you get two completely different answers. Okay, so if you minimize it in, say, W12, you'll get this red curve. If you minimize it in W1p for some p bigger than something or other, you will get the blue curves. Actually, there are examples now in the calculus of variations. Foss constructed an example of a two-dimensional problem where the infimum of the energy in every Sobolev space W1p for any real p bigger than 1 or something is different. Okay. So these examples show you that the function space that you are minimizing over is part of the model. It must be part of the model, because if you change the function space, you get different predictions. Right? So, of course, this is not a physical model, but it's illustrative. Anyway, so that's all to say as to why it is that it's not so obvious that that this is true. You can't just argue from the fact that the integrand is going to be infinite somewhere. So how do we do it? Well, it's a sort of, you can do it two ways. You can do it by a sort of maximum principle, but there's a sort of slightly more efficient way of doing it, which uses the structure of the single constant theory. So what you can do is you can sort of approximate the set where f is finite, which is some convex set of q's, at the boundary of which we're hoping to get blow up, by this set k epsilon, which is the set where f is less than or equal to 1 over epsilon. And then you take some q, which you imagine does not have the minimum eigenvalue bounded away from minus a third, and you take the nearest point projection onto this convex set. And you show that, well, because the thing is blowing up at the boundary, it's not surprising that when you take the nearest point projection, it will reduce the energy. But you have to show that, of course. And then, by a piece of very good fortune, the elastic part reduces also. Okay, and this wouldn't be the case. It isn't the case if you have more general elastic terms, and that's why this particular method doesn't extend to more general terms. But anyway, if you have so effectively, this means that if you're outside this set and you do this projection, you get something else which has strictly less energy. So that's a kind of contradiction. So that's how we do it. And for this nonlinear elasticity problem, I regret to say that that's much more difficult. So we don't even know how to do the liquid crystal one in all its generality. But this one, so why is this one more difficult? It's more difficult, well, for various different reasons, but it's more difficult because here the constraint is on the top order derivative, whereas in our case it's on the on the Q tensor, and we have derivative terms to help us. So, but here it's on the actual top order derivatives. And well, there's lots of other sort of kind of more topological reasons why this is very tricky, but this is anyway a completely open problem. And that means that, for example, in nonlinear elasticity theory, if you try to minimize the total storm, well, we have various theorems which say that the minimizer of this exists, say, for example, for various models of rubber or something like this. And so the sort of the most straightforward form of the Euler Lagrange equation we cannot derive in we don't know that the minimizer satisfies the most sort of straightforward form of the Euler Lagrange equation in weak form. There are other weak forms that we do know under certain circumstances are satisfied of the equilibrium equations. So I think that's all I'm going to say, right? Oh, just that this seems to be very difficult. Okay.
Yeah.